All right, so lesson number 21, acids and bases. This is posted May 22nd. This is the last lesson in this section. So test number 3 will be 13 through 21. All right, so on the day this is posted, homework number 18 is due. Next week, May 25th through 29th, is a little bit short because of Memorial Day on Monday, so nothing's going to happen then. But on Wednesday, we have quiz number 3, review 3 on Friday, and then homework number 21 is due via Sapling on Friday, May 29th. Test number 3 is Monday, June 1st via Sapling. Make sure I put up a video just with some tips, etc., similar to last time, but I specifically give some information on what's going to be on quiz number 3. All right, so last time we talked about acids and bases and figuring out pH. And one of the things we talked about was percent ionization. Remember, percent ionization is, for acids, it's the concentration of H plus over the concentration of acid. But there are some keys to this. It's always H plus at equilibrium over the acid I have initially. Right? So in this problem, if I have 0.85 molar HF and it ionizes, this 0.85, that's my initial. So that's what's going to go on the bottom. So I'd have 0.02 over 0.85 times 100%. And that gives me 2.4%. That would be my percent ionization. Is this a weak or strong acid? It's a weak acid. Why? Because strong acids, this would be 100%. Okay, because that's the definition of strong acid. All right, so let's go ahead and move on. And let's talk about pH of weak bases. Last time we talked about strong acids, strong bases, and weak acids. Now we're going to talk about weak bases. And then we're going to talk a little bit more about something called polyprotic acids. So when we have a weak base in water, such as NH3, what happens? Well, some of that NH3 gains an H plus to become NH4 plus. But notice I still have some of that original base in there, right? So it doesn't fully form NH4 plus, right? I have a little bit of both. In the same way, if I had a weak acid like HF, I form F minus, but I still have HF left over. Okay. So if I were to find the pH for a weak base, I'm gonna have to use the concentration of the base, Kb, and I'm gonna have to use an ice chart. All right, so let's look at a problem. Let's say we have ammonia, and we want to know its pH of a 2 molar NH3 solution. Okay, we're told NH3, we're told it has Kb. This B stands for base. So that means this must be a base. And notice this is 10 to the minus 5. That's a small number. So this must be a weak base. So what that means is NH3 is going to gain an H plus, because that's what bases do. What does it gain that H plus from? It gains it from water. Okay? And once it gains that H plus, it's going to form NH4 plus. But this is equilibrium. Why? Because it's weak. Okay? All right, so that's going to leave me with OH minus. So I'm going to have NH3, that's ammonia, plus H2O gives me ammonium and OH minus. So I can go ahead and I can do an ice table with this. Initial change equilibrium. Initially I have 2 molar of this. I don't care about the water. I have 0 molar of that NH4 plus. And I actually have some OH minus to begin with, because this is water. I always have OH minus if I have water. But we're just going to assume it's 0, right? This is so small, we assume it's 0. All right, so I have my initial. Now I go ahead and I plug in to find my Q. And it's going to be 0. Why? Because I have 0 times 0 on top. So my Q is 0. My K is 1 times 1.8 times 10 to the minus 5. So that means it's going to shift towards the right. So that means these are going to increase. This is going to decrease. All right. So now that I have this, I can go ahead and plug it into my equation for K of K equals x squared over 2 minus x equals 1.8 times 10 to the minus 5. Okay. Can I assume that x is small? Well, I can assume it because both of these are small numbers. So that means I'm going to assume that 2 minus x is equal to 2. Okay. So that's going to be x squared over 2 equals 1.8 times 10 to the minus 5, or x equals the square root of x squared, which is the square root of 3.6 times 10 to the minus 5. Right? I multiplied this out, got this, and then take the square root. And this is going to get me my value. Let's go ahead and see this. 3.6 e to the negative 5. Square root that, I get 6.006, or 6 times 10 to the minus 3. Either one is fine. That's my value for x. Now I can go ahead and I can use that. Okay, so this would be 2 minus 0.006. It's going to get me 1.994, or just 1.99 molar. This is going to be 0.006 molar, and this will be 0.006 molar. Okay, now let's go ahead and just check and make sure we did this right. So K would be 0.006 squared over 1.99. I get 1.81 times 10 to the minus 5. So I'm really close to what I started with, so I'm good. Okay? All right. Now, I could also check my assumption. You always should. But in this case, I'm not going to. This lesson is long enough. We're not going to go in it. But you can. And we see that 2 and 1.99. Yeah, that's really small difference. Okay. But notice what this asks for. This asks for the pH, right? Last time I did a problem, I got a value and I just found that pH from that. But notice, this is OH minus. So I can't find pH from this. What I have to do is I need to use this equation to figure out my H plus, because that's what's going to give me my pH. So H plus equals 1 times 10 minus 14 over 0.06. Okay? And that's going to give me my H plus concentration, 1.67 times 10 to the minus 12. I now do negative log of this. That's going to give me 11.8. Does this make sense? I start off with a base. I should get a basic pH. Okay. All right, let's go ahead and look at this on the screen. So I start off with my equation. Right? That's always key. I have to have a reaction. Then I go ahead and put it in an ice table, figure out my change, and then figure out my x. In this case, my x is equal to my OH minus. So I then have to calculate H plus and then finally pH. Okay. I should check my assumptions. In this case, they're both valid. And so I'm good. Okay. Now, notice in this case, we assume that 2 minus x was small. What if I can't? Well, then I have to do the quadratic, okay? And that's going to be more difficult. Actually, in the video problem you're going to do, you're probably going to have to use the quadratic, okay? All right, so let's go ahead and let's just review. For lesson number 20 and 21, we went over strong acids and strong and weak acids, strong and weak bases, okay? If I have a strong acid, I can just assume it fully dissociates, find that H+, and find pH. If I have a strong base, it fully dissociates, so I can figure out my OH-, plug that in to get H+, and then plug that in to get my pH. If I have a weak acid, I'm going to have to use an ice chart. If I have a weak base, I'm going to have to use an ice chart. If I use a weak acid, I can calculate an H+ directly from it, and I can calculate pH. But if I have a weak base, I need to convert that OH- to H+, and then figure out pH. All right, let's go ahead and one thing I did not talk about is, remember, we can also, from that weak base, we could figure out the percent ionization, right? Remember, percent ionization is going to be dependent on the amount of, in this case, the Hb+, right? The amount of ionized value and the amount of initial base. Let's go back and just do this real quick. So in this case, right, I started off with 2 molar NH3, and I ended up with 6 times 10 to the minus 3 for my NH4+. So my percent ionization would be 6. Let's do it on the board. My percent ionization would be 6.0 times 10 to the minus 3 over my initial times 100%. Okay. It's always times over what I initially had. And that's going to get me 0.3%. Okay. So it would be good. Right? Or that means it'd be a weak base. All right, let's also on the board just go through some of this just to remember. Okay? So if I have a strong acid, remember what a strong acid is. A strong acid is one that fully dissociates, right? So that means all of my acid gets turned into H+. An example would be if I had 0.5 molar HCl. All of my HCl would get turned into H+. Right? And now, if I want to find pH from that, I can just do negative log of 0.5, and that's going to get me my pH. In this case, that would be 0.3. All right, that's for a strong acid. Let's say a strong base. Okay. For a strong base, we know that all of my base goes to OH-. Okay. Oh, by the way, what's a strong acid? Well, there's something you should know. HCl, HI, HNO3, H2, so forth. These are all strong acids. These have big Kas. Okay? Strong bases have big Kb's. Examples are NaOH and KOH. Okay? And so, for example, for this, if I have 0.5 molar NaOH, I'm going to go ahead and I'm going to get 0.5 molar OH-. Okay? And so then I can use Kw equals H+ times OH- to calculate H+, and then use that to get pH. Okay? All right, weak acids, these have small Kas. Okay? An example is HF. Okay? Well, if I have my acid concentration, I'm going to have to use my Ka in an ice chart to figure out my H plus concentration. And then I can just go ahead and find pH. Okay? If I have a weak base, such as NH3, this has a small Kb. I'm going to take my base concentration, use its Kb and the ice diagram to find the OH minus concentration, convert that to H plus, and then finally pH. Okay. All right, so let's go ahead, and this is on the screen. Let's go ahead and show you video problem 21A. Video problem 21A is all about ionization of a weak base, right? So I have HS minus, and I want to know the reaction involved, right? Notice it has a Kb, so that means it's going to gain an H plus, right? So what happens if HS minus gains an H plus, right? And it's going to gain it from H2O, so what's that going to leave behind? Okay? Go ahead and figure out the 4 species present at equilibrium. What are the equilibrium concentrations of these? What is the pH of this 0.04 molar HS minus? And then finally, what's its percent ionization? All right, so go ahead, do that, and then we'll look it over in that problem. Okay, so we just got done talking about finding pH of acids and bases. So far, everything we've been talking about has only produced one hydrogen. Okay, so let's go ahead and now let's talk about some special ones, or special acids and bases called polyprotics. Okay, polyprotics have multiple. All right, so let's go back and remember what an acid is. An acid is a compound that donates H plus to another compound. What this means is that you must have a hydrogen to be an acid. Okay? If I don't have a car, I can't donate to Cars for Kids, right? I need a car to donate it. Okay? And so let's say I had HCl. HCl can go to form H plus and Cl minus. Okay? This is a strong acid, so we say it's only one way, right? In fact, its Ka is really large. Okay? This hydrogen that we see here is called an acidic hydrogen, right? It's a hydrogen that gets dissociated, right? This hydrogen goes away. Okay? Not every hydrogen is acidic, right? So for instance, CH4, right? If I put it in water, none of these hydrogens go away, right? I don't form CH3 minus and H plus, right? They actually figured out the Ka for it. The Ka for this is 1 times 10 to the minus 56, right? What does that mean? I have very little H plus in comparison to CH4. So small it doesn't even happen, okay? So CH4, we would say it has no acidic hydrogens, okay? The reason why CH4 has no acidic hydrogens is because of the chemistry. And you'll learn more about this in OChem, okay? All right. Oops. So if we have a compound or an acid that only gives up one H plus, we call this a monoprotic acid. Okay? This could be because it only has one hydrogen. HCl only has one hydrogen, so it's monoprotic. Or it could be that it has multiple hydrogens, like this compound CH3CO2H, right? It's right down here. It only has one acidic hydrogen, right? This hydrogen is going to go away, and I'm going to be left with this compound. But none of these other hydrogens will dissociate. They're all going to stay attached, right? The reason for this is structure, but we would say that these hydrogens that don't leave can be called non-acidic hydrogens, okay? All right, so that's monoprotic. We can also have polyprotic. Polyprotic are acids that have more than one acidic hydrogen. They give up more than one hydrogen. We can have diprotic, which is 2, or triprotic, which is 3. We could also have tetraprotic and pentaprotic, but those are fairly rare, and you won't have to worry about those until biochem. Okay? All right, so polyprotic acids produce more than one H+. An example is H2SO4. H2SO4 is at the bottom there. Right? I have a sulfur, 4 oxygens, and 2 hydrogens. It goes ahead and it loses one of these hydrogens to become HSO4. Because it's losing an H+, it's now negative. Okay? This compound here can then lose a second hydrogen to become SO4 2-. Right? It lost another positive thing, so that makes it more negative. Okay? This is called stepwise ionization. This doesn't happen in one step. It's one reaction and then another. Okay? So we can write these two reactions. So the first ionization, losing the first hydrogen, is H2SO4, goes to form H plus HSO4 minus. This we signify by Ka1. Okay? Ka1 is losing the first hydrogen. Our second ionization would be taking this compound, HSO4 minus, and losing another hydrogen to become SO4 2 minus. We call this Ka2. Okay? Ka1 is losing the first, Ka2 is the second. Now, in the past, the last couple lessons, we've just been talking about Ka and Kb. That's because we've only been dealing with monoprotic acids, okay? But for diprotic, we have Ka1 and Ka2. Okay? All right, notice, by the way, that Ka1 is bigger than Ka2. The reason for this is, if I take away a hydrogen from H2SO4, I end up with a negative compound. To take away an H plus from this negative compound is going to be tougher, right? Because that negative is going to want to keep that H plus, okay? So I'm going to get less of that second ionization occurring. All right, so let's have you guys do a problem. So we have H2CO3, and we're told it's a diprotic acid. And we want to know the first and second ionization reactions, and then what are those Ka expressions. Okay, I took a little break, which is probably a good thing for you guys to do when you're feeling, in these lessons, oh my goodness, this is horrible. Take a break, come back stronger, okay? That's the nice thing about these being pre-recorded. Make sure you're in good headspace, right? There's no point to have this when you're not able to learn, right? I needed to because I was not able to teach right then. All right, so I needed a little bit of a break. Okay, so we have polyprotic acids, right? So for instance, H2CO3, it loses an H plus and then forms HCO3 minus, and then that loses an H plus to form CO3 2 minus. These are Ka1, Ka2. Notice Ka1 is much bigger than Ka2, right? That's always the case, and usually Ka3, when there is one, is smaller, okay? Now let's think about this. If I have a glass here and I put in H2CO3, okay? What's going to happen? That H2CO3, some of it is going to fall apart to form HCO3 minus and H plus. But because it's a weak acid, some of it remains as H2CO3. Okay? Now what's going to happen? Now I have some HCO3 minus, and that's going to fall apart to give me CO3 2 minus. Okay? But I'm still going to have some of the HCO3 minus. I'm still going to have some of that H2CO3 from the initial one. I'm going to be producing more H plus, and so I'm going to have all 4 of these compounds in there at equilibrium. And I'll have one other compound in there of OH minus. I'm going to have OH minus because this is all aqueous. So if it's aqueous, that means there's water, and water always forms H plus and OH minus. Okay? And I also have 2 different producers of H plus. I have this one, and I have this initial one, and I have this one here. Now it turns out that the initial producer of H plus is always going to be the bigger of the 2, right? It's going to be the primary producer of that H plus. The reason being is that is your Kas, right? Notice that Ka1 is so much bigger, so it's going to produce way more H plus. All right, so let's go ahead. Oh, and in fact, if Ka1 is greater than Ka2 by order of 20, right? So Ka1 over Ka2 is greater than 20. That means that I can assume all the first H plus is all the H plus is from the first ionization. All right, so now let's move on and let's do a problem. So let's say we have 0.033 molar of this H2CO3. Okay? We're told it's a diprotic acid, and we're given its Ka1 and Ka2. So we want to figure out what all those equilibrium concentrations are. Okay? So I have 2 equilibriums. So what does that mean? I get 2 ice charts. Yay. Okay? And we're going to go through this, and then I'm going to show you a little bit of a shortcut, but it's good to start with this. Okay? All right, so I have H2CO3 going to H plus and HCO3 minus. So I'm going to start off same way I've always have with my ice chart. Okay? I'm told I have 0.033. Now, initially I have some H plus, but we're going to assume it's very small, and we have no HCO3 minus. So my Q is going to be H plus times HCO3 minus over H2CO3. So that's just going to give me 0. Why? Because I have 0 times 0 on the top. All right, so if my Q is 0, and my K is 4.3 times 10 to the minus 7, that means it's going to shift towards the right. But also notice that both these are small, so X is small. All right, so if it shifts towards the right, plus X, minus X. Okay, so 0.033 minus X, I have X, and I have X. Okay, all right, so now I can go ahead and plug these in. So Ka1 equals X squared over 0.033 minus X, sorry, equals 4.3 times 10 to the minus 7. Okay. I already said that these both are very small, so I can assume that X is small. Okay. I should go back later and I should check this to make sure. So this would be X squared 0.033 over 0.033 equals 4.3 times 10 to the minus 7th. X squared equals some value. (1.4) times 10 to the negative 8. Okay. I'm going to go ahead and I'm going to take the square root of this. That's going to give me x. So now x is equal to 1.19 times 10 to the minus 4. Okay, that's my value for x. So now I can go ahead and plug that into here. Okay, my h plus is 1.19 times 10 to the minus 4. My HCO3 minus is 1.19 times 10 to the minus 4. And this will be 0.033 minus 1.19 times 10 to the minus 4. And that's going to get me a small number, or not a small number, but a 0.0329, right? A small change, okay? All right, so these are my 3 concentrations so far. So far, we've only used that first equation. Now we need to go ahead and we need to use the second equation. Why? Because now that I have some HCO3 minus, it can go ahead and it can react to form CO3 2 minus. Okay? All right, I'm going to save some of these. Oh, so I'm going to just move this one over here just for safekeeping. Because now we're going to use that second equation. Okay? And our second equation is HCO3 minus goes to form H plus CO3 2 minus. This has a Ka2 of blah, 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 5.6 times 10 to the negative 11. All right, and so I have to do another ice table. But what do I start with? This is my HCO3 minus. Not this value, right? Because this is H2CO3. So I can go ahead and that's where I start. And notice my H plus is also, I don't have any of this, okay? So my Q is going to be this times this over this. Well, that's just going to be 0. My Q is 0, my K is slightly bigger, so it'll shift towards the right. So plus x, minus x, 1.19 times 10 to the minus 4, minus x, x, and x. Oh, sorry, 1.19 times 10 to the minus 4 plus x and then x. Okay. Now I can go ahead and I can go on to my next step, right? So I do ice table 1. I then plug in my answers into this one. Okay. All right. I'll show this again on the screen so you have it. Now that I have these equations, I can go ahead and say Ka2 is going to be this. Times this over this. Equals 5.6 times 10 to the negative 11. Okay? So now I can go ahead, oops, this is minus x, okay, because this is minus x. Now I can go ahead and I can think my Q is 0, my K is 5.6 times 10 to the 11. So what does that mean? X is small, okay? They're both smaller than 0.01. So if x is small, I'm going to assume that this minus x is just the same as this number. But I'm also going to say that this plus x is also just equal to this number. Okay? Why? Because it's like, I always say, you know, if Donald Trump, he's a billionaire, he gives me $1, that doesn't change the fact that he's a billionaire. But in the same way, if he's a billionaire and I give him $1, which is probably more likely, he's still, his net worth doesn't change. He's still a billionaire, right? So if X is so small in comparison to this, right, adding or subtracting it doesn't matter, right? So I'm going to assume two more things. That this plus X is just equal to 1.19 times 10 to the negative 4. And that 1.19 times 10 to the negative 4 minus X is equal to 1.19 times 10 to the negative 4. Okay? All right, so if I do that, this becomes a lot simpler. So it's 1.19 times 10 to the minus 4 times X over 1.19 times 10 to the negative 4 equals 5.6 times 10 to the negative 11. Oh man, these are the same numbers. They just cancel out. So X equals 5.6 times 10 to the negative 11. Okay. Now I can go ahead and I can use that here. Okay. That's my amount of CO3 2 minus. Okay. 1.19 times 10 to the negative 4 minus this, or plus that, is still going to give me the same. And this minus that still going to give me the same. Okay. All right, so what are my final answers? I get 5.6 times 10 to the minus 11 molar CO3 2 minus, very small number. I have 1.19 times 10 to the minus 4 molar H plus, 1.19 times 10 to the minus 4 molar HCO3 minus, and I have from the very beginning 0.0329 molar H2CO3. Right? So I start off with 0.033 molar H2CO3. A little bit of it formed these, and then a little bit of this formed this. Okay? All right, these are 4 of these species present. There's one other species present, OH minus. Okay? So I can figure out OH minus from this. It's going to be 1 times 10 to the minus 14 over this value, and that's going to get me a small number. 8.4 times 10 to the minus 11 molar OH minus. Okay. All right, so that is that for figuring out the species present. Okay. I could also use this to figure out pH. Let's just do this real quick. I can take the negative log of that, and that would get me 3.92. Okay. All right, let's go ahead and look at this on the screen. So I start off with one ice chart. I can go ahead and calculate from that. So I start off with one ice chart. I figure out what the value of Ka1 is in terms of X. I then can solve for X. In this case, I could assume that X is small, right? I plug that in, and that's going to get me my concentrations of the species in my first equation. I can then plug these values in to my second ice chart, right? Notice H2CO3's concentration doesn't go into the ice chart. Why? Because it's not in the second equation. Okay. All right, and then I could solve for X and blah, 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 right? Now there is one simplifying thing, and that is I can assume that X is so small that the second reaction isn't going to change it, right? So I could just go ahead and say that my H plus and HCO3 minus are going to be the same. The second equation doesn't change anything. And my concentration of the CO3 2 minus is just going to be equal to the Ka2. Okay. All right, so these are my values. I can use it to versus Ka1 and Ka2 to make sure everything is ready. I can also figure out the concentration of OH minus there and the pH. Okay. All right. That was for a polyprotic acid. That was for a diprotic acid. We also have triprotic acids. Triprotic acids are ones that produce 3 H+. An example is H3PO4, also called as phosphoric acid. It is going to go ahead and lose one hydrogen, then a second, and then finally a third. Okay, so let's just do this on the board. If I start off, don't need all this. If I start off with H3PO4, I'm going to lose an H+. That's going to make this H2. PO4 minus, right? Because I'm losing something positive, so that makes me negative. And then that's going to go ahead, minus, and lose another H+. And that's going to get me HPO4 2 minus. And then that HPO4 minus, 2 minus, is going to lose another H+ and become PO4 3 minus. Then that PO4 3 minus, it can't lose another hydrogen because it doesn't have a hydrogen. Okay? All right, so notice the only thing that's changing is the number of hydrogens and the charge. Okay? I don't change the PO4 in any way. This is Ka1, Ka2, and Ka3. Now, Ka1 is always going to be bigger than Ka2. It's always going to be bigger than Ka3. Okay? And if I put H3PO4 into solution, I'm going to get all of these compounds at equilibrium. Okay? Plus, I'm going to have one other compound, and that's OH minus, because it's always there. Okay, so that's polyprotic acids. We can also have what we call polyprotic bases. Polyprotic bases are just the opposite of polyprotic acids. They're the conjugate bases, right? So polyprotic acids donate more than one H+. PO4 polyprotic bases accept more than it. So if I have PO4 3 minus, it can accept a hydrogen. It accepts it from H2O to form HPO4 2 minus. That's going to leave behind OH minus. Then that HPO4 2 minus can take another H plus to form H2PO4 minus. Then that H2PO4 minus can take another hydrogen from H2O to form H3PO4. Right? This is a polyprotic base, right? It adds one hydrogen. This we call KB1, KB2, KB3. KB1 is always greater than KB2. It's always greater than KB3. And let's look at something. This compound HPO4 minus, 2 minus. Here, it's an acid. Here, it's a base. Okay? So here it's losing an H+, here it's gaining an H+. This is an example of what we call an amphiprotic compound. A compound that can be an acid or a base. Okay? HPO42- is an example in this one, but we can also think of acid as being both an acid and a base. Okay. All right, let's go ahead and have you guys do a problem. This is video problem 21C, where we're told that CO3- is a diprotic base. What are the chemical equations for the first and second ionization? Okay. All right. So that is pretty much it for polyprotic acids and bases. I just want to talk about one thing real quick, and that is when we have acids and bases, we should know what's going to happen. What species are we going to get at equilibrium? And this all depends on whether it's monoprotic or diprotic or triprotic, and the values of those Kas and Kbs. Okay? So if we have a strong monoprotic acid, right, that means Ka is large. Okay? What's going to happen? That acid, such as HCl, is going to fully dissociate. So that means at equilibrium, I'm not going to have any of that original HCl. If I have a strong monoprotic base, like NaOH, it's going to fully dissociate, and I'm not going to have any of the original base left. Okay? This would be a large Kb. Okay? Notice whether I have an acid or a base, I'm still going to have some H plus and OH minus. There'll be different levels, but they'll still be there. All right, if I have a weak monoprotic acid, it's going to go ahead, such as HF, it's going to produce some HF plus and some F minus, but I'm still going to have some of that HF left over at equilibrium. That's because it's a weak acid. If I have a weak monoprotic base like F minus, it's going to form some HF and OH minus, but I'm still going to have some of that F minus left over. Okay? That would be if it has a small Kb. All right, so these are monoprotic. Let's think about, oh, by the way, notice that in both these cases, whether I started off with F minus or I started off with HF, in both cases I end up with the same species, right? So in a lot of times it doesn't matter which I start with, I'm still going to have the same species because it's at equilibrium, okay? Because it's reversible. All right, if I have a polyprotic acid and I want to know what's present at equilibrium, well, this depends a lot on the Ka, right? So if I have a small Ka1, such as for H2S, that H2S is going to form some HS minus and H plus, but it's still going to be there. And then that HS minus is going to form some S2 minus, okay? I'm also going to have some OH minus left over. Okay? Now this is going to end up the same as to whether I add in S2 minus or HS minus, right? I'm always going to have some equilibrium, some reactions going in all these ways to make sure I have all 5 of these present. Okay? Now if I have a polyprotic acid, but it has a large Ka1, this is the case with H2SO4, which is a strong acid, it's going to fully dissociate to give me HSO4 minus and H plus. That HSO4 minus is then going to dissociate to get me SO4 minus, right? So at equilibrium, I'm going to have all these species, but I'm not going to have any H2SO4. The reason is that that H2SO4, it's strong, so it fully dissociates. Okay? All right. So that is it for polyprotic acids. We went through, we talked about Kas, Ka1s, Ka2s, Kb1s, Kb2s, and we talked about the reactions involved. I'm not going to require you for a test or for homework to be able to do the calculations, okay, for polyprotic acids. For monoprotic acids and monoprotic bases, you do need to know those. But polyprotic with the multiple ice tables, you don't have to know. All right, so that is it for lesson number 21 and the end of this section on acids and bases. Remember, test number 3 will be lessons 13 through 21, and that's going to be on June 1st. All right, go ahead, start remembering there's a quiz, and then there's a review next week, and then homework number 21 for this lesson is due Friday, May 29th at midnight. All right, bye-bye.